So, just as a brief introduction, my name is Chinmoy, and I'll be presenting the session for you, which is a 1 hour session divided into four small parts. At the first, I'll just have a brief intro about excavation. Then, the second part will be a brief intro of GTS Annex, and then we'll discuss the problem statement and go to the numerical model. And meanwhile, towards the end, you can have the Q&A. So, meanwhile, if you have any particular questions that you would like to be addressed, I'll request you to note down the questions on the question panel, and I'll be able to answer them one by one towards the end of the session. Okay. Now, so so starting with a brief intro to excavations. So when we say excavation, what is an excavation? So as a definition or a scientific terminology to mean, it is just the generic process of earth removal to form a cavity in the ground. And any excavation should encompass or encapsulate all the activities that involve the removal of either rocks or soil or plant debris, or what we also called as stripping, either by mechanical means, or if the trench is quite narrow, sometimes jackhammers also do the job. And the main intention is either reuse of the material or any further construction on the excavated zone. Excavation can be classified based on different characteristics of the excavation. So basically the type of material or the objective of the excavation. So on a broad scale, excavation can be classified into two different types. First, by type of the material excavated, the topsoil excavation, or what we also call as topsoil stripping. Then earth excavation, it can go deep. Then rock excavation, either the outcrop rock or the outcrop of a hill, or if let's say the top surface is a rock. Or muck excavation. Muck excavation is basically done where the water level is quite high and the soil is of horrible quality. So in the material from muck excavation cannot be reused for anything. It has to be dumped somewhere. So basically, it's like excavating either clay or highly cohesive soil or silt. And then some can also be termed into the unclassified types. And then coming to the purpose of excavation. So if we classify the excavation based on the purpose they solve, first is the cut and fill excavation. It is quite evident, and you might have seen it in the urban areas. So especially where, let's say, subway station have to be built. Sometimes we dig the area and then it is backfilled along the precasted segmental liners. And then trench, basically trenching are thin, low width, but the depth may vary. It can go to higher depths too. So either for pipelines or cables or underground water supply systems, or they may solve a multitude of purposes. Then third is basement excavation, which is quite common in the urban area. Fourth is excavation for road. Fifth is excavation for dredging. So dredging essentially is in the high seas. Then finally, it is the over excavation. Now coming to a few geotechnical issues associated with excavations. So what kind of geotechnical issue we can think of? Well, a lot of things can go wrong if we are, if we are using geosciences and our study or our interpretation of the particular science is not 100% complete. So I use the word complete. I did not use the word accurate because it is very hard to 100% replicate the ground behavior. So what we can do is we can try to approximate the best or the worst possible outcome. If not, you will end up with something as shown in the pictures. Like on the top left picture, if I just show you, you can see a part of the road embankment has collapsed along with the and taking the retaining wall with it. Similarly, in the bottom, you can see a contiguous board pile wall with extremely good backup support system of bailing and anchoring. Yet you can see along the corner where the machine or the excavator is standing, the area has completely failed. Now, this particular image is indication of two things. First and the foremost thing is that the excavations need to be planned very carefully and meticulously. Second, this example is the classic example of why we would need a 3D analysis to support our vision. Because you see, this thing failed in the corner. So, to prevent this effect of extra stresses, concentrating on the corner, we need to go for the 3D analysis and then take a look at how the stresses are getting accumulated and also how the wall elements or the support elements are behaving according to the prevalent ground conditions. So this is the main reason why I showed this particular picture, because this is the indication of how a 3D analysis need to be done or why a 3D analysis need to be done. And not to mention, here it is a we can say that these contractors are a bit lucky that there is no high-rise apartment complex in the vicinity. Let's say if there was one, then there might have been chance when the entire complex would have been evacuated. So these are certain issues which are valid for excavations either in rural areas or in urban areas or let's say in unmanned areas too, that one needs to be taken care of. So with this part being clear, we have finished the first part of the session. That was brief intro about excavations. Now I'll tell you a bit about GTS NX, then we'll go to the problem statement. So with GTS NX, first and the foremost thing for us will be to see the ground topography development. So for ground topography development, GTS NX supports a multitude of features. So you can either import your contour maps, soil stratigraphy data or borehole logs in DXF, DWG, parasolid format, and you can use either the point face option or the terrain geometry option, terrain geometry maker option to create a comprehensive face as seen on the bottom right picture. Now, the top left picture here is a contour map which can be developed into a proper topographical 3D face in GTS NX with the use of the inbuilt geometrical tools. Otherwise, if you have a large area, which is also called as a stringed or a triangulated area, which is basically an output of either a GIS software or let's say softwares like Leapfrog or Minex or Vulkan or Surpac. In those cases, you can also export these kind of large triangulated digitized string surfaces to GDS and get done with your faces. And actually, Civil 3D is also right now able to make these kind of stringed faces for large area distribution. Next, you can import your total station points, or you can also import points from Google Earth via the Excel format, and you can develop the face right away with the aid of the software automation tools as shown in the right picture. Otherwise, You can also import your LiDAR survey or Landsat survey data, and you can get your DEM or digital elevation model. The digital elevation model is available in two formats. One is the format where you get the elevation of all the points along the survey area, or DEM phase can also look like the previously shown triangulated face. So both way it is possible, and both of the things can be imported into GTS, because right now instead of total station, drone photogrammetry and LiDAR are taking the front seat in terms of surveying and automation and data image processing. In those cases, those inputs can provide a comprehensive development of a face in GTS, which can then be meshed, and you can continue with your analysis case in here. Then after your soil topography or the ground topography has been developed in GTS, the next thing will be to create your borehole layers. So for that, we have the bedding plane wizard, where all you need to do is just input the layers depth, and you can get your borehole distribution looking like this. So if we imagine or we take a concept from the field and we want to reduce that in a reality, it will appear something like this. So first we took up a concept, and then we mapped the necessary area, and then using the automation features provided in the software, we can have a comprehensive 3D model looking like this. Next, the interoperability of GTS NX. So any software, it should be able to be compatible with any structural platforms. So fortunately, in our case, GTS is extremely compatible with inputs from MIDAS Civil and MIDAS Gen. So here you can import your entire bridge or your apartment complex or your plant or a transmission tower, anything that is a structure in that is a structural model, along with all the loading conditions, they can be completely imported into GTS, and then you can go with the comprehensive ground analysis or the soil structure interaction. So if we secondly imagine the same concept to reality, you can see for a structural foundation analysis, like in here, you can import it into GTS and you can see the effect of the structure on the existing ground. Same thing goes for the bridge foundation analysis too. So now we'll see certain type of analysis types and applications of GTS. So GTS NX is basically all-in-one FEM based axisymmetric 2D and 3D integrated platform for geotechnical analysis. So in the very same software, you can do all three: axisymmetric, 2D, and 3D. So in terms of the analysis types, you can start with a static analysis. So a non-linear static or a linear static. Then for slope stability, we have the strength reduction method or the CFI reduction method. We have the LEM or the limit equilibrium method. Then we have the construction stage for slope stability. For example, if you are excavating a hillside, and with excavation your factor of safety changes, and you want to take a look at various deformations of the slope along with the slope factor of safety, you can go with the construction stage methodology for the slope stability. Then we have the dynamic analysis. So here you have the eigenvalue and response spectrum analysis, linear nonlinear time history analysis, or equivalent 1D or 2D linear analysis. And GTS also supports the stress seepage coupled nonlinear time history analysis plus slope stability SRM analysis. So basically, let's say if you have a dam or you have a cofferdam or a retaining wall, and you have, let's say, water flowing from one head to the lower head, or let's say you are dewatering your excavation zone, and then at that point of time, let's say seismic wave is acting. In those cases, you can do the nonlinear time history with the stress seepage coupled, and you can check for the change in the ground behavior due to the earthquake waves hitting the static condition of groundwater drawdown. Then you can do the seepage analysis, a steady state or a transient state seepage. So steady state is basically, let's say you have a retaining wall and your groundwater is flowing from behind the retaining wall to your excavation zone. And transient state seepage is basically, let's say you are lowering your groundwater level or you're having a groundwater drawdown by the use of pumps or wells. In those cases, you can go for the transient seepage. Next is the coupled analysis. So GTS supports both semi-coupled and fully coupled analysis. Then we have the consolidation analysis for soft ground. And to support that, we have materials like soft soil, modified jam clay, etc. And finally, if we combine all of the analysis types, we will end up with the construction stage analysis. So we can do the drained, undrained analysis, seepage for each step, or a coupled analysis. Then you can also do the fully coupled analysis in the construction stage methodology. You can check for consolidation independently of each stage if required. And you can also check for cons pre and post consolidation slope factor of safety in using the construction stage analysis methodology in GTSMX. So now we take a look at a few of the application areas. So starting with tunnels. So you can do both 2D and 3D analysis in GTS as mentioned before. The top left picture where you have a portal with a fractured zone or a shear zone on the longitudinal section or on the section of your tunnel progression. You can go for a 3D analysis using GTSNX. Otherwise, the combination of ventilation shafts plus access tunnels to the main subway system, including the cross passage, can be modeled. Or you can model something like a shield TBM progressing through the urban areas. So cities like Singapore or Kuala Lumpur or Manila or Mumbai, mainly Southeast Asia, the urban areas are still expanding. So TBM is the preferred use of choice for tunneling. So in those cases, you can go for the complete analysis of the ground behavior and the structural behavior based on the the progression of your shield TBM. Otherwise, for a tunnel in a hill, you can go for the the steel pipe reinforced step grouting. And you can see here the tunnel has a very varying overburden. The overburdens are different at the portals, and it has lowered due to the valley depression just at the middle of the tunnel. Then you can also check for the construction of two new TBM tunnels below an existing NATM tunnel, which is below the basement of a high-rise tower and the presence of the bridge foundation elements as shown in here. So the main study that was done in this model was to check for what kind of extra stresses are developed or what is the externally induced shear zone or plastic zone around the foundation piles and also the pile caps for the bridge foundation due to creation of the new up and down tunnels. Then you can go for the subway tunnel with four poling or crown improvement. So next is excavation and temporary structures. It's just something we are going to cover today. So you can go for either a diaphragm wall or a contiguous board pile wall or a sheet pile wall, or you can check for the impact assessment for your existing infrastructure due to the construction of your, let's say, subway system or a basement for high-rise tower. Then for foundation, you can go for a simple raft footing or a pile raft foundation or a well foundation. Then for ground improvement, you can do the breakwater analysis or the soft ground improvement using prefabricated vertical drains or sand drains. Then revetments or quay walls or otherwise stone columns as shown in here with a 3D model. So this is the chart you are seeing here is the long-term settlement chart due to the loading uh, imposed by the hydrocarbon tank. Then the slope stability analysis, the C5 reduction method. Then the LEM method. The chart you see here is the chart for your slope stability analysis using LEM for different operational conditions of an earthen dam. So the first part, you can see the factor of safety is quite high because these are normal operating conditions. Then the factor of safety starts dropping in the rapid drawdown scenario. So if I just change my pointer to a pen marker, you can see this is the scenario of the rapid drawdown. It starts from here and goes till here. So in this range, the factor of safety drops from around 2.2 to just 1.3 at the final stage of drawdown. So this is basically coupled analysis where you go for the water drawdown from the upstream side and you check for the upstream slope stability. And then we have applied this hydrostatic force in here. And in pseudostatic, the factor of safety drops from around 2.2 to 1.6. Then result of seepage analysis. So you will have phreatic lines as shown in here. This is the example of acceptable or a good phreatic line, which means water is flowing from the inside of a soil matrix or a dam as it should. Then if we have water flowing like this along the dam embankment, then yes, we have a problem, which essentially means your dam is not functioning as a dam anymore. Due to that region, the flow is quite high and the dams are made of earthen materials. So, which essentially means that high pore pressure along with external or excessive seepage as a result will also lead or also might cause liquefaction of the core material. And if this is the second case, so case one, that is acceptable case, case two, not acceptable, case three is piping or piping developed due to internal erosion. So you can see this total height here of the dam is around 120 meters. And this fall, this side is 90 meters. So if the water falls to a height like this, you can only imagine what is going to happen. The water will develop piping and you will have either blowouts along the downstream or sinkhole formation. So these are basic, engineering interpretations which you can deduce out of GTS. So the shoulder movements of a dam and the liquefaction, phreatic lines, factor of safety variation. Finally, for mining and geotechnical engineering, 2D or 3D open pit mines, then your underground haulage road plus crosscuts. You can basically call it as, a labyrinth of tunnels underground. Then your waste storage, then dumps and stockpiles. So I hope this is the applications of GTS are clear for everyone. Next, we are gonna check out the numerical model, and then go to the we'll go to the numerical model and the software demo itself. So in terms of problem statement, this is my excavation. The excavation is around 25 meters wide. Okay. And for excavation supports, we have five stage supports: one, two, three, four, five. So basically, wheelers and struts are the support systems. And the entire numerical model looks like this. So the whole point of making the model big are there are two regions. First and foremost thing is your stresses and your plastic boundaries around the excavation should not reach the outer boundary, because it will give you wrong results in that case. Now, similarly, along with the lateral boundaries, the total boundary should also be deep enough. So in this case, it's around 50 to 75 meters. And we have also applied the interface element to simulate the relative slip between the retaining wall or the diaphragm wall and the soil. So there are two ways of, there are multiple types of constitutive materials available for simulating this. But here we have chosen the more column for now. Then the modeling methodology. So first thing is you create the geometry or you import the geometry. In our case, I just imported the geometry. If you have a drafting team with you, it is always better to import your geometry. It works much more faster. Second is we define the material properties. So let's say for steel, for concrete, for soil and rocks, we define the materials. Then we define the element attribute property, either 1D, 2D or 3D. So here the ground elements are 3D, the diaphragm wall is 2D, and the strutting and the wheeling system are 1D elements. Then we define the mesh. So you can have either tetra mesh or hybrid mesh in GTS. So then we have the loading and boundary conditions where we apply either the static loads or the dynamic loads or any boundary conditions like your constraints or pinned supports or seepage boundary conditions. Then we do the analysis and finally the result. So in terms of results, so what do we see? Here our goal was to create the excavation, check for the excavation deformation along with the impact assessment of local areas. So the one of the ways of doing that is by checking along the trend line what is the extent of deformation as you move far away from the excavation. So here you can see as we move far away from the excavation, the total settlement is around minus 0.37 mm, minus zero point 0.4, minus 0.10. So, and the values are in mm. So we can say that we have designed in this case only, not it's not applicable for every case, that in this case we have designed a very sturdy support system that prevents the 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 soil in the vicinity to be getting extra stresses, or the soil around the vicinity is not getting extra shear use. Now, the forces on the wall, they look like this. The by forces, I mean in this case, it is the bending moment along the wall. Okay, you can see the bending moment is extremely high along the corners. Isn't that what we saw at the very first of in the beginning of this presentation, that how that particular excavation failed along the walls? Then this is the total depth of the wall, and then the total deformation along the line. Then the axial load on the studs and the valves. And it goes without saying that most of the load should be taken up by the strutting system. Whaling system is more or less to ensure that the load is distributed uniformly along the length of the wall element. So I believe everyone enjoyed the presentation. Now we'll go to the software demo. So this is the model result, but since this is a big 3D model, it takes some time to run. But before going at the results, and this is the results I'm going to show you, we are just going to create our model ground up. So for that, I'll click on the drop down menu, click on new. I'll create a 3D model. So the top option is the ribbon menu. In the left, you have the work tree menu. You have the model or the inputs like geometry or your mesh control, and your loading conditions, then your boundary condition, and then your analysis sets, and then your results. This is the work pane, so anything you do it will be visible in here. And in the bottom you have the output pane. And one more thing that is very interesting about GTS is the fact that it has a multi-tabbed window. So you can open 10 different models and run 10 different models at the same time. But please do note, it also depends on your computer's hardware capabilities. So I'll now import my geometry. So I'll click on import CAD file. So we have multiple amount of CAD imports possible, which I'll show you right away. But you can also import the DXF and DWG, both 2D and 3D. Now, in terms of CAD imports, you can import Parasolids, ASICS, STEP, IGS, CATIA versions, then SolidWorks or Unigraphics or Inventor files. So the range of import is quite huge. Here I'm going to import a Parasolid file, this one. So you can see this is my numerical model. My geometric looks like this. Okay. So if I go to the geometry drop down menu, if I hide the solids, you'll be able to see the reinforcement system. Okay. like this. So what I'll do is I'll remove a couple of things which I do not need in here. So the bottom one and then the top lines I don't need. So I prefer keeping a clean geometry as long as possible. So which is why I prefer only keeping the items which I find absolutely necessary, only to retain those and do and nothing else. So this is my support frame. Okay, the whalers, then the struts. So basically my geometric part has been imported completely. And then if I hide this, you'll see my excavations. One, so barring these two, these are my main excavations. One, two, three, four, five, six, seven. So with a total excavation depth of 15 meters and width of 25 meters, length of 25 meters. So 25, 25, 15 is my actual excavation depth. And apart from that, my embedded depth of the wall will be 5 meters. Now, the embedded depth of a wall depends upon a lot of factors, like the width of the wall, the type of soil or rock which is there, the type of excavation. These are certain things, and also there are codes where it has been they have defined, certain country codes have clearly defined the minimum required length of embedment. So but again, most of the government agencies are now becoming quite open to interpretations from numerical models, be it finite element models or discrete element models. So in this case, the finite element model is what we are going to calculate. So the excavations and then the soil around it. Now, before going for the meshing, I need to define my materials. So either you can define your materials or you can also import your materials. Since I had told you that I have already run the model, so I have my materials predefined. So GTS automation feature of importing your material and element attributes helps you save a lot of time, because we do not need to recalculate anything or we do not need to re-enter anything. Once the material have been defined, you can just import them from another model. So I'll go to property, I'll use the import option. So what I'll do is I'll just click on my model and you can see everything has been defined here. So I'll just import all of them, drag and drop. Topsoil, medium sand, dense sand, bedrock are my layers of soil. Various struts, D-wall, and the base slab. I'll press OK. Now, here you'll see, since I only imported the property, but the properties have been derived from a material type. So along with the properties, the materials will also be imported. So I'll go to material. You can see this has been imported in here. Now to create a new material, we'll go to isotropic and you can select the model type or the constitutive model type. So we have the elastic materials in here, and then we have the von Mises, Tresca, and then for soils we have Moorcoulomb, Trockerprager. For soft soil we have the S clays, modified cam clay, soft soil creep. For liquefaction modeling we have your UBC sand, Nor sand, PM4 sand, and bowl model. For hysteresis soil models, we have hardened Renovich, Rambia Gosgut, or Sekiguchi Ota. And then for concrete or to simulate cracks in concrete, we have concrete smear crack and concrete smeared plasticity. And for purely for excavations, we have not only hardening soil with small strain stiffness, we also have we also have the modified Moore column. And for rocks, we have Moore column, Hook and Brown, generalized Hook and Brown, and CWFS. So CWFS means cohesion weakening, friction strengthening. That is the long-term behavior of rocks in excavations. So my topsoil is of depth 4 meters. Then my second layer is medium sand, has a depth of 6 meters. Third is a dense sand with a layer of around 7.6 meters. Fourth is fractured schist with a depth of 12 meters. And fifth is my highly weathered schist that is depth of 20 meters. Now, fractured schistose rocks are extremely weak. So they possess very low bearing capacity and they sometimes they also need like reinforcements. They come under the category of rock persists are one of the worst quality rocks which are available in the nature. So because cystose basically means crystalline formations on existing rock. So it can be a metamorphic rock or it can be a sedimentary rock. Now, due to these crystallizations, the rock inherently becomes very crystallized in format, and these are notorious for chemical weathering and disintegrating due to water flow around it. So basically, schistose rocks or gypsum or limestone, they are not exactly the, I would say, an ideal scenario for any construction. They need deeper study to rectify or understand what kind of behavior to expect out of it. Now, with that being cleared, I'll just show you the property of the diaphragm wall. So it is a 150 mm diaphragm wall of concrete with the veilers having the section property of a rectangle like this and the struts. So, or you can also, create your own properties. That is not a big issue. You can just go to section and create whatever section you want. We have a multitude of properties. So, section properties like ASTM standards, the British standards, or the Korean and the Canadian. This is the Canadian standard, then the Indian standard. So, in terms of section property definition, all you need to do is just enter your data in here. The stiffness coefficients will be calculated by the software. So now what we do is we create the numerical model. Okay. So my model is here. Now I just create my numerical model now. So starting with the meshing, what I'll do is I'll hide the outer solids, okay, and also the 1D elements, and I'll go to mesh 3D. So I'll select the size as 1. So this is my excavation 1. So I'll choose the layer as topsoil. Okay, 1, 2. Then I come to medium sand, 3, 4. Okay. Then from this layer, it will be dense sand, or my sixth excavation is in dense sand. 7th is also in dense sand. 8 is into dense sand. And ninth, or the final, this is not an excavation layer. This is, we have just created the block so that it's easier for us to extract the retaining wall. This will be my Sisto's rock. Press apply. Okay. So my excavations are now meshed. Next part will be meshing my soil elements. So I'll click on the topsoil and name it as S1. Sorry, my bad. I should have given a bigger mesh size. So first layer is S1 because the mesh size should be within the range of file to course depending on what exactly are you looking for. So you can see it is quite fine along the excavation zones, but towards the boundary it becomes more coarser. Then my second layer is medium sand. So I just name it as S2. Then my third layer is dense sand. My fourth layer is rock, and so is my fifth layer. Now after this, we'll create our structural elements. So we have only created the ground elements now. Time to go for the structural elements. I'll hide everything and I'll go to mesh, extract. I'll go to top part. I'll extract the sides because we have already meshed them. So I just need to extract the elements to create my wall. Now wall is a 2D element or a shell element with a predetermined thickness of around 0.15 meters or 150 mm. It can be even higher. So I name it as D wall like this. Now I hide the wall and I only activate the, and this will be my formation of the base slab. So just below the 7th excavation is our base slab. So I select the property as base slab and I name it as base slab. Okay, see. Now, so my D wall and my base slab are complete now. Now I'll create my 1D structural elements. So for that, I just activate my curves. And again, as I've told before, if you don't need certain things, feel free to delete them. I've always that follow that principle. It makes my job, pretty easier that way. So in this case, I'll just delete these lines which I don't need. I only need the framework here. So that is what I'll keep like this. Or I can also delete the lines along the edges. These edges. I do not need them too. So I'll just delete them. Okay. Now we'll now mesh the struts. So we have to keep it in a view which is clear for us to understand and see properly. Now I'll go to 1D and I'll start selecting my objects. Okay, like this. So if it is sometimes hard for you to directly see, you always feel free to rotate the objects. You can either do it that way, or the second way is just go to top view and hide the wheelers for now so that only these struts are visible, right? See, only the strutting layers are visible. So here it is easier for us to select. So I'll go to create only. The number of divisions will be 1. I name it as ST. So my first layer being ST1, ST2, 3, 4, 5. Okay, my starting is complete. Now the veiling systems. So if I hide my mesh and I just go to top view and I ensure that only my veiling system is visible, I'll right click and press show only. You can see only the veilers are visible now. So I'll mesh them the very same way I did with the strutting. So I'll enter the division as 1. So name it as veilers. So this is W1, W2, W3, W4, W5. Okay. So you can see my starting veiling system, my base slab, my diaphragm wall. Okay. Now we create the interface for the wall. So I'll select the diaphragm wall. I'll go to interface and I'll select as plane interface along the shell element. I'll select my shell element here. And since it is mostly sand, we take a stress reduction factor ranging from 0.6 to 0.75. And please do note, when we take non-linear interfaces, they are also elements with non-linear properties, which means they will have a finite stiffness. If that stiffness is breached, the model might diverge. So here I take a value of 0.7, press OK, and I'll press OK. It will take a couple of seconds. You can see my interface. So my model inputs are really there. I just need to define the boundary condition. So I'll go to static slope analysis, constraint, auto boundary, press. Okay. So my model is built up and ready. I just define the construction stages now and I'll run the analysis. So I'll pan the model to the right, like you can see here, and I'll start defining my cases. So here in the bottom, you can see in the show data, there is nothing activated. So I'll activate my 5 soil layers, my rigid link, and the excavations. Then the boundary condition, then the loading condition. We'll press save. Now, please remember, whenever you have interface, always use a rigid link, because when the interface is not active, then the mesh nodes need to be connected via the rigid link. Otherwise, the model may or may not converge. So it is as a standard practice or SOP, it is always better to create an interface create a rigid link when interface element is created. So next, we install the wall. So with the wall comes the plane interface. So I activate the plane interface and then the diaphragm wall. Press save. Third will be my first excavation. So I deactivate the excavation wall. You can see here, save. Then the excavation 2. Same thing, I deactivate the excavation 2. Press save. Then my first level of supports will be installed. So I'll activate the ST1, then the W1. For a more clearer view, let me just hide the interface. Okay, so it's a bit easier for you to see. Then excavation 3 after my first level of support. Okay, then excavation 4. Then the second support system. So W2 and struts. Then excavation 5 on the deactivated segment. Then the third layer of support. Then excavation 6 is deactivated. Then the fourth layer of support, that is failure 4 and ST4. Then the final excavation. Okay. And then the final layer of support. Then after everything is excavated, we just install our base slab and we are done with the construction stage like this. Okay. So then we just run the model. Now, the fun fact is GTS allows two kinds of mesh sets, the tetra mesh or the hybrid mesh. So this model was created using the hybrid mesh, but the analysis results that we will be seeing is along the tetra mesh. The main difference being that the hybrid mesh drastically reduces the total number of elements required. You can see the total number of elements are around approximately 50,000. Now, if we take a look at the total number of elements in the tetra mesh, you can see it is right now around 7 times higher. So this is where GTS comes with the advantage that we boast an analysis time that is at least 30 to 40% faster than any competitive software available in the market. Due to the sheer virtue that we are able to reduce the total number of elements by a factor of 7. So which is huge in terms of, like time saving, but the results will be exactly the same. So coming down to results now, for the wall stage, the total ground deformation due to installation of the wall is like this. Just a moment. Oh, yeah. So this is excavation 1. Just a moment. Sorry for the interruption. Yeah, we are back. So excavation 1, then the second excavation, the total deformations. So in the excavation boundaries, you can see along the bottom, you might be able to see a bit of heaving. Then the TX and the TY translation. Just a moment, it's loading up. Some issue. Let's try to fix that. Yeah. So the TX translation along with the vectors. Yeah, all good now. So let's say I just go to any random stage of support. I go to excavation 5 and I look for the action loads on the beam elements. They will look like this. Okay. So I'll just hide the results for now. I mean the outer soil layers. So here you can see. So with the seek bar itself, you can see what is the change in the deformations or the forces along the entire length of the model. So along the base slab installation, if we see the forces now, you see the entire distribution from top to bottom. So let's say I hide my soil layers for now. Okay. You can see the forces on the whalers and the struts. And again, if I hide all the whalers, you'll see how the struts take up maximum amount of the load. So since this is a big model, it takes a couple of seconds for the results to load up. You can see here, if I use the value option, the maximum load is along the top, and the bottom we go, the lower is the load taken up by the support system. So one can argue the bottom support system is not required. Yes, that is true. In this case, the bottom support system is not required because most of the load is taken up by the struts and the whalers on the top. Similarly, if we want to see for the the strains along the excavations, if I go to solid strains and check for shear strains, so we have the option called as the clipping plane, where you will be able to see in the middle of the model. So this is my exact range. So here you see, if I activate the origin, so my wall starts exactly at the origin, and here I know that until the length of 25 meters, this is my excavation, okay, and this is the area where the excavation influences the local site, okay, and it can be seen either from the X and also from the Y direction, like this, okay. So the shear zone due to excavation is very close to the vicinity of the excavation, approximately 1 or 1.5 meters. Beyond that, there is not much of a difference. So this is how the excavation looks like from the Y direction. And you can see the shear zone formation along the boundary of the wall and the retaining elements. So basically, we can say that thanks to the support system in here and also thanks to the ground material in here, whatever excavation was created, the entire impact is contained very close to the vicinity. So let's say I just pick up probing points and I want to see the ground deformations. So this is, let's say, 0, 1, 2, 3, 4. You can see the shear you can see the strains localization, the shear strains, the value is quite low, which should be the case because the higher it is, the higher is the chance of collapse. Here we are getting around 1% shear zone close to the vicinity, and it is a good thing that there is a retaining wall which is able to restrict the movement of the soil. If the same number would happen anywhere near the new legends that we are creating, then this would have been a problem. So the impact assessment basically means how far is the spread of your disturbed zone from the boundary. So which is clearly visible by using first the probe option and second the option of uh, the clipping plane. So to take a look here, and I see it like this. So this is my total length of the area that is disturbed. So for today's session, This was what I had planned to show all of you. Now, if you have any questions, please feel free to ask.